Live output from subprocess command. I'm using a Python script as a driver for hydrodynamics code. When it comes time to run the simulation, I use subprocess.popen to run the code, collect the output from stat and stare into a subprocess.pipe, then I can print, and save to a log file, the output information, and check for any errors. The problem is, I have no idea how the code is progressing. If I run it directly from the command line, it gives me output about what iteration it's at, what time, what the next time step is, etc. Is there a way to both store the output, for logging and error checking, and also produce a live streaming output? The relevant section of my code. Originally I was piping the run_ command through T so that a copy went directly to the log file, and the stream still output directly to the terminal, but that way I can't store any errors, to my knowledge. My temporary solution so far. Then, in another terminal, run tailflog.txt, stlog_file equals log.txt.
TLDR for Python 3, he. You have two ways of doing this, either by creating an iterator from the read or readline functions and do. Or you can create a reader and a writer file. Pass the writer to the popen and read from the reader. This way you will have the data written in the test.log as well as on the standard output. The only advantage of the file approach is that your code doesn't block. So you can do whatever you want in the meantime and read whenever you want from the reader in a non-blocking way. When you use pipe, read and readline functions will block until either one character is written to the pipe or a line is written to the pipe respectively.
Executive Summary, or TL, Doctor version. It's easy when there's at most one subprocess.pipe, otherwise it's hard. It may be time to explain a bit about how subprocess.popen does its thing. Caveat, this is for Python 2.x, although 3.x is similar, and I'm quite fuzzy on the Windows variant. I understand the POSIX stuff much better. The popen function needs to deal with 0 to 3 IO streams, somewhat simultaneously. These are denoted stin, stout, and stare as usual. You can provide none, indicating that you don't want to redirect the stream. It will inherit these as usual instead. Note that on POSIX systems, at least, this does not mean it will use Python's sys.stout, just Python's actual stout. See demo at end, an int value. This is a raw file descriptor, in POSIX at least. Side note, pipe and stout are actually ints internally, but are impossible descriptors, -1 and -2, a stream, really, any object with a fileno method. Popen will find the descriptor for that stream, using stream.fileno, and then proceed as for an int value, subprocess.pipe, indicating that Python should create a pipe. Subprocess.stout, for stare only, tell Python to use the same descriptor as for stout. This only makes sense if you provided a non-none value for stout, and even then, it is only needed if you set stout equals subprocess.pipe. Otherwise you can just provide the same argument you provided for stout. For example, popen ... stout equals stream, stare equals stream. The easiest cases, no pipes. If you redirect nothing, leave all three as the default none value or supply explicit none, pipe has it quite easy. It just needs to spin off the subprocess and let it run. Or, if you redirect to a non-pipe, an int or a streams file, no, it's still easy, as the OS does all the work. Python just needs to spin off the subprocess, connecting its stin, stout, and or stare to the provided file descriptors. The still easy case, one pipe. If you redirect only one stream, pipe still has things pretty easy. Let's pick one stream at a time and watch. Suppose you want to supply some stin, but let stout and stare go unredirected, or go to a file descriptor. As the parent process, your Python program simply needs to use write to send data down the pipe. You can do this yourself, for example. Or you can pass the stin data to proc.communicate, which then does the stin.write shown above. There is no output coming back, so communicate has only one other real job. It also closes the pipe for you. If you don't call proc.communicate, you must call proc.stin.close to close the pipe, so that the subprocess knows there is no more data coming through. Suppose you want to capture stout but leave stin and stare alone. Again, it's easy, just call proc.stout.read, or equivalent, until there is no more output. Since proc.stout is a normal Python IO stream, you can use all the normal constructs on it, like or, again, you can use proc.communicate, which simply does the read for you. If you want to capture only stare, it works the same as with stout. There's one more trick before things get hard. Suppose you want to capture stout, and also capture stare but on the same pipe as stout. In this case, subprocess cheats. Well, it has to do this, so it's not really cheating. It starts the subprocess with both its stout and its stare directed into the single pipe descriptor that feeds back to its parent, Python, process. On the parent side, there's again only a single pipe descriptor for reading the output. All the stare output shows up in proc.stout, and if you call proc.communicate, the stare result, second value in the tuple, will be none, not a string. The hard cases, two or more pipes. The problems all come about when you want to use at least two pipes. In fact, the subprocess code itself has this bit. But, alas, here we've made at least two, and maybe three, different pipes, so the count none returns either 1 or 0. We must do things the hard way. On Windows, this uses threading.thread to accumulate results for self.stout and self.stare, and has the parent thread deliver self.stin input data, and then close the pipe. On POSIX, this uses poll if available, otherwise select, to accumulate output and deliver stin input. All this runs in the single parent process/thread. Threads or poll/select are needed here to avoid deadlock. Suppose, for instance, that we've redirected all three streams to three separate pipes. Suppose further that there's a small limit on how much data can be stuffed into a pipe before the writing process is suspended, waiting for the reading process to clean out the pipe from the other end. Let's set that small limit to a single byte, just for illustration. This is in fact how things work, except that the limit is much bigger than 1 byte. If the parent, Python, process tries to write several bytes, say, go \ntao proc.stin, the first byte goes in and then the second causes the Python process to suspend, waiting for the subprocess to read the first byte, emptying the pipe. Meanwhile, suppose the subprocess decides to print a friendly hello. Don't panic. Greeting. The H goes into its stout pipe, but the E causes it to suspend, waiting for its parent to read that H, emptying the stout pipe. Now we're stuck. The Python process is asleep, waiting to finish saying go, and the subprocess is also asleep, waiting to finish saying hello. Don't panic. The subprocess.popen code avoids this problem with threading or select/poll. When bytes can go over the pipes, they go. When they can't, only a thread, not the whole process, has to sleep, or, in the case of select/poll, the Python process waits simultaneously for can write or data available, writes to the process's stin only when there is room, and reads its stout and or stare only when data are ready. The proc.communicate code, actually _communicate where the hairy cases are handled, returns once all stin data, if any, have been sent and all stout and or stare data have been accumulated. If you want to read both stout and stare on two different pipes, regardless of any stin redirection, you will need to avoid deadlock too. The deadlock scenario here is different. It occurs when the subprocess writes something long to stare while you're pulling data from stout, or vice versa, but it's still there. The demo. I promise to demonstrate that, unredirected, Python subprocesses write to the underlying stout, not sys.stout. So, here is some code. When run, note that the first routine will fail if you add stout equals sys.stout, as a stringio object has no file no. The second will omit the hello if you add stout equals sys.stout since sys.stout has been redirected to os.devnull. If you redirect Python's file descriptor 1, the subprocess will follow that redirection. The openos.devnull w call produces a stream whose file no is greater than 2.
We can also use the default file iterator for reading stout instead of using iter construct with redline.
In addition to all these answers, one simple approach could also be as follows. Loop through the readable stream as long as it's readable, and if it gets an empty result, stop. The key here is that redline returns a line, with \n at the end, as long as there's an output and empty if it's really at the end. Hope this helps someone.
Review 我更新了，并分析了自己。